Okay. Okay. So today we will discuss Master's theorem, which will be important for tomorrow's quiz. So the rules for there are three rules for the Master's theorem. So the first thing is that given a function Tn equals to a Tn, maybe just give me a sec. Mhm. Tn equals to a times T of n by b, this plus big O of n to the power d. If you see something like that, one function for which nth term can be expressed this way, then you can find the runtime quickly using Master's theorem. So Master's theorem says that the runtime of Tn will be big O of n to the power d, given d is greater than log a base b, or it will be big O of n to the power log a base b if d is less than log a base b, or it will be big O of n to the power d log n if d is equal to log a base b. Okay, so do you have any confusion regarding this theorem? This will be critical for tomorrow's quiz. We will go over some examples to discuss this theorem in details, but it will be important for the quiz tomorrow. So make sure that you properly understand it. Okay, so let's discuss one example for the Master's theorem. Suppose, suppose it is given that Tn is equals to 5 times T of n by 4 plus n. So, yeah. So here we can see that here A is equals to 5, then B is equals to 4, and T is equals to 1. So we have a relationship between T and log of A base B. So here we can see that T is less than log of A base B. That is 1 is less than log of 5 base 4. Therefore, the runtime of this given algorithm will be Tn will be big O of n to the power log A base B from Master's theorem. So we can directly apply this case here as d is less than log A base B. So directly from Master's theorem, we can get the answer for the runtime of this algorithm, which will be big O of n to the power log A base B. Okay. So similarly, okay, any question from this theorem?
Yeah, on the first part,
Mhm.
on the where it says D above D less than log base B A, what does that say? It's
Yeah,
like
this
D
part?
and? Yeah.
Yeah, and that's and we have to find the relationship between D and log A base B, because in Master's theorem you can see that the runtime directly depends on the relationship of D and log of A base B. So if D is greater than log of A base B, then it will be big of n to the power D.
Hmm.
And if D is less than log of A base B, then it will be big of n to the power log A base B. And if they are equal, then it will be big of n to the power D log n. Yeah. So is it clear?
Kind of, yeah.
Yeah. So uh, I can't hear you clearly. Is anyone speaking?
I think somebody has their mic unmuted.
Oh, okay. Okay. So one easy way to remember the Master's theorem is that whichever term is greater will go to the power of n. If d is greater, then it will be n to the power d. And if log a base b is greater than d, then it will be big of n to the power log a base b. And if they are equal, then the runtime will be big of n to the power d times log n. It is one of the tricks to remember the Master's theorem. And one other thing is that Master's theorem will only apply if the runtime is expressed in this way. If you can express the nth term as a times tn by b plus big of n to the power t, then only you can apply the Master's theorem. Otherwise, it will not be applicable. Okay, so let's discuss one other example. So,
Can you scroll up a bit? Sorry.
mhm, yeah, sure. Mhm. Any question?
No, I just didn't get the chance to write the bottom part.
Okay. Mhm. So, yeah, let's discuss one other example. Then I will give you a few more examples to solve by yourselves, and I will send you to the breakout rooms where you can discuss among yourselves how to solve the example using Master's theorem. Okay, so for the second example, let's consider Tn is equals to 7 times Tn by 7 plus n squared. So here we have d is equals to 2, a is equals to 7, and b is also equals to 7. Okay, so the relationship between d and log of a base b is, so first of all, log of a base b is equals to log of 7 base 7, which is equals to 1. So as 2 is greater than 1, therefore we can write d is greater than log of a base b. So by applying Master's theorem, we can directly say that Tn will be big of n to the power d, which is equals to big of n square. So this will be the runtime for this given algorithm. Any question? Any confusions regarding this one?
Could you show the down?
Okay.
Thank you.
Is it okay? So yeah, let me give you 3 examples, and I'll give you 5 minutes in the breakout rooms. Then we will discuss the solutions here. So the first one is T of n is equals to T of n by 2 plus 1. The second one is T of n is equals to, so it's a open book, so you can use the internet or any other resource if you want. So and it is also not graded, so don't worry about the grades. And tomorrow's quiz will be graded, so you just have to practice master's theorem for tomorrow's quiz. So feel free to ask any questions, confusions that you have regarding the master's theorem. The third one is T of n is equals to T of n by 3 plus n. Or one fancy way of saying that is T of n is equals to T of n by 3 plus big O of n. This is same thing as just n. Okay, so I am giving you 5 minutes in the breakout rooms. So we will meet here at 1:22. Okay, so welcome back, everyone. So, anyone want to give the answer for number one? The running time for number one. Any question regarding number one?
For number one, I got the big O of n to the 1 log of n.
Yeah, exactly. 12 big of n to the power 1 log of n. Because d is equals to log of a base b. It's correct. Okay. So for number two,
Excuse me.
yeah, go ahead.
Could you write the D, A, and B for the first one?
Okay, so
D.
d is 1. Uh,
D is 0, I think.
oh, yeah, exactly. D is 0.
That,
D is
that
not
means
1.
I just have a question.
Mhm.
What's happening?
Yeah, yeah.
Now it's
But
changing.
yeah, it is not log of n log n. D is 0, A
A
is
is
2,
2, B
and
is
B
2.
is also 2. So D is less than log of A base B. So it will be big of n to the power log of A base B, which is big of n.
Why is D 0?
Because here it is given 1, right? So you can say that it is equivalent to n to the power 0. Is it clear? Because n to the power 0 is equals to 1.
Yes.
Mhm. Yeah.
Excuse me.
Yeah.
For number one, after that kind of things, you said it's equal to O N.
Yeah,
Oh,
because log of A base B is 1. Log of 2 base 2 is 1. So it will be big of n.
oh, okay, I got
Mhm. Yeah. Any other question regarding this one? Okay, so for number 2, anyone wants to give the answer for number 2?
you.
For number one, so the running time was O of n then?
Yeah, yeah, it is of n. Big of n. It comes from this one. Big of n. Okay, for number 2.
For number two, we need to just figure out D, A, B. The D is 3, the
Mhm.
A is 8, the B is 2.
Yeah,
That,
exactly.
that means 3 is less than log 8 in 2. That means the answer is O N D log N.
Uh, yeah, exactly. D is equals to uh,
B is
so D is 3, A is 8, and B is 2. So D is equals to here log of A base B, which is uh, 3 is equals to log of 8 base 2, because as it is also it is 3, not 2, it's 3. So the runtime for number 2 will be is equals to big of n to the power d log of n, which is equals to big of n to the power 3 log of n. Yeah. Mhm.
we always need to, the last part, we just put the number and just get it. For example, O n power of 3 log n. If you write it n power of d log n is not correct.
And power d log n, yeah, it is also correct, but you have to put the value of d to give the final answer. So
Oh,
this is the formula, right? You have to put the value of the exact variable here to get the final answer. This is the general formula. This is not the final answer. I think she might deduct some marks if you leave it there. It's always better to give the final answer.
Okay.
Excuse me, maybe I have written down it wrongly. Can you show the master theorem again?
Okay, yeah, sure.
The last one.
There.
So the last one, big O of n to the power d log.
N.
After log, it is a or n.
N, it's N,
Okay,
not A.
that's why. Sorry.
N.
Okay, thank you.
Mhm. Okay, welcome. So now for number 3. Anyone wants to give the answer for number 3? Anyone?
For number 3, I got ON.
Yes.
PN equal ON.
Yeah, exactly. You are correct. So can you identify A, B, and D for number 3?
So I got A equal 1,
Yes.
B equal 3,
hmm
and D equal 1.
Yes, exactly. So here we get D is greater than log of A base B. That means 1 is greater than log of 1 base 3. Therefore, it will be big O of n to the power d, which is big O of n to the power 1 or big O of n. So yes, you're right. Okay, so okay, let's discuss 2 other examples.
Excuse me, I have a question.
Yeah, go ahead.
I remember the previous class, the professor said in a quiz, you must figure out that kind of the formula is a kind of working or not working. Could you just,
Yeah,
the example is not working, we can use that kind of things for that one.
yeah, exactly. Let's discuss those examples now.
Yeah, I was gonna ask, like, she said, like, we could determine whether or not it would apply, the master seat would
Yeah.
apply.
Exactly. So I'll give you 2 examples and then 5 minutes to discuss those examples among yourselves. Then we'll discuss them here. Okay. So the first one is T of n is equals to T of n minus 1 plus C to the power n. Assuming that C is greater than 1, C is any constant which is greater than 1. Okay. And number 5 is that T of n is equals to T of n by 3 plus T of 2n by 3 plus C of n. Same C is some constant greater than 1. So we will meet here at 1:36, and I will send you to the breakout rooms now.
I didn't get a good look at question 3. Can you scroll up a bit? I'm sorry.
Yeah, sure.
The
Answer for 3?
No, I got the answer, but not the question
Oh,
itself.
the
Yeah.
question. Okay, so this one.
Yes, that one. T of n. Okay, thank you.
Okay.
Excuse me, in the number 5, is it c to the power n, the last one?
Now c times n.
Okay, c times n.
Mhm. Okay, so anyone wants to discuss number 4? What is A, B, and D here?
I don't think it would apply, would it?
No, it would not apply. Uh,
D is N. We can do it.
mhm. D is actually not n. For applying Master's theorem, you have to get something in this form. Mhm. The equation has to be in this form. T of n is equals to A times T of n by B plus big O of n to the power d. If the equation is not given in this form, then you cannot apply Master theorem.
That
Uh,
means after the plus is constant, we can imply that kind of thing.
No, it's constant to the power n. So
Hmm.
it has to be n to the power something.
But if it's opposite, is n to power of something, we can imply that kind of thing. right?
Yes, yeah. And here also it is n minus 1, not n divided by something. So although you have A here, but you don't have B. And you also don't have D. So you cannot apply Master theorem on number 4.
So
Yeah, go ahead.
for the Master theorem, basically to get the b, it have to be divided by divided something
Yeah.
and
N
the power,
divided by something.
yeah. And for the d, it have to be something of power of n.
N to the power something.
Yeah. Thank you.
Okay. So for number 5, anyone wants to discuss number 5?
We are getting 2a in the number 5, right? No, value is same, but it is two different value, correct?
Yeah, you cannot apply Master theorem
There
in
also.
number 5 too, because you have multiple equations of n here.
Okay.
Yeah, so Master theorem doesn't apply. It has to be a single equation of n. A
Function of n
times
have to be different. Same.
n by b. Yeah. So if it is multiple equations, then you cannot apply Master theorem. So for this example, also Master theorem doesn't apply.
Is it possible they give us something and we can merge that kind of two things, and after that we get one equation?
Can you repeat your question?
For example,
Mhm.
they give us two equation like Tn to 3 plus Tn to 3. But we can just merge these two things and get one thing.
Yes. If they're exactly the same, then you can merge them. But
You can say, and then you can say like 2t or 3t or whatever.
yeah, so here for the next term, it will not match up. T of n. Okay, let's discuss that. It is given T of n is equals to T of n by 3 plus T of 2n by 3 this plus C times n. Okay, so for the next term, T of n by 3, it will be T of n by 6 plus 2 times T of n by 6 Not this 2 is inside. 2 times t of 2n by 6 plus c times n. So if, as you can see, the value of b is here 6, but the value of b for this one is 6 divided by 2. Similarly here, it is the value of b is 3 and it is 3 divided by 2. So the two b's don't match, right? If the 2 was outside, then you could have merged them. But here the value of b is different for these two terms. So you cannot merge them.
Thank you.
Is it okay? Is it kind of clear why you cannot merge them?
Yes.
Okay, thank you. So now let's discuss iteration. Another way of solving the equations is by considering iterations. So for example, if we have t of n is equals to t of n by 3 plus big of n. You can apply Master's theorem there directly. One other way is by using iteration. So there you can consider the next term. What will be next term if we put n by 3 there? So then it will be t of n by 3 will be t of n by 3 square plus c times n by 3. So we are writing this big of n as c times n, which are the same thing. C of n will be big of n. And then the next term will be n by 3 square, which will be t of n by 3 cube plus c times n divided by 3 square. Okay, so we can write t of n will be t times n by 3 cube plus c times n divided by 3 squared plus c times n divided by 3 plus c times n. Is it clear? We are getting these constants right from those equations.
I'm sorry. How did you transition from t of n over 3 squared over times t of n?
Mhm. So I just put n by 3 in this equation. So if you put n by 3 here, you will get this equation. This equation.
Yes, and then we
Written-
went to n over 3 squared because
Yeah.
we did it again.
Yeah, we did it again.
Oh, so now we're just going back to the n.
Yeah. So
Okay.
we are putting these values in the original equation. Then we'll get this equation. Does it make sense?
Yes, thank you.
So then we'll get one equation like that. And then the general term will be t of n is equals to t of n divided by 3 to the power I, this plus cn divided by 3 to the power I minus 1 plus c of n divided by 3 to the power I minus 2 plus all the way to c of n divided by 3. No, actually c of n plus c of n. Yeah, this will be the final term. So does this make sense? It comes from this one, We are generalizing it.
I just had a question. I mean, I don't know. I didn't get the step after n over 3 squared. Like, I don't know why we didn't go to like n or over 3 cubed, or like, how do you even know where to stop? Is my question.
Yeah, exactly. That's what we are trying to find. So I showed the first two terms for this equation, n over 3 and n over 3 squared. Then we generalized it. So n over 3 to the power I. So then we will find one term where we can stop. So is this transition kind of clear? How we are getting from this equation to this equation? We're
Yeah.
just
Like, what would be the difference between like using I and after this using n? Like, what's the difference?
so I is any general term for which we can express this equation as this one. If we put the value of I as 3, then we'll get that equation. This will work for any value of I. Is it clear? Kind of.
In the fourth line, how did you bring the tn again?
Mm,
In the fourth line.
This
Yes.
one?
Yeah.
This one? Okay. So we are putting the value from these two equations to the first equation. Then we get this equation. We're
How
putting
we
the
are
value of
putting the value? Okay.
Mhm.
Yeah, we have put
Yeah.
it there.
there,
And
and this one goes there.
okay.
Finally, we get
Okay. Okay.
this equation.
Can you say that again? I still don't get it.
Yeah, so we are putting the value of t of n over 3 in this equation.
Mhm.
Then the value of t of n over 3 square in this equation.
Mhm.
So if we add up all these three equations actually, then we'll get this fourth equation.
Okay.
You can
And
put
can
the
you
value
use like
here.
4 or 5 or 6 if you wanted, or?
Yeah. So that's why we have generalized this equation.
Oh,
To
okay.
get,
So we can stop whenever we want, but as long as we just need to see a pattern first, and then we can generalize it. Then?
Exactly. Yeah.
Okay.
Yeah. So this is the general form which this equation is following. So then we will assume that for some given t, 3 to the power t is equals to 1. No, n divided by 3 to the power t is equals to 1. As you can see that the value of 3 to the power I is increasing as we increase the number of iterations. So for example, at the beginning it was just n divided by 3. Then if we consider the next term, it was n divided by 9. Then it was n divided by 27. So can you see the pattern here? The denominator is increasing as we
Yeah.
progress in this equation.
Yes.
So we will,
What? Why would it need to equal to 1 again? Like n over 3t, 3 to the power of
yeah,
t.
so we will assume that n over 3 to the power t is equals to 1 so that we can get the final answer for this equation.
How do you get 1?
Yeah, then if it is 1, then we will stop repetition because for t to the power n, if t to the power n over 3 to the power t is equals to 1, then we cannot apply any further repetition for I, as the term I disappears from it. Do you get it? For example, before if t to the power 3 to the power 9, it was from that equation, from the original equation. T n over 3 to the power 10, this plus c times n divided by 3 to the power 9 from the original equation. But if we get some t for which t to the power t of n divided by 3 to the power t is equals to 1, then we cannot apply this formula again. It stops there. Do you see what I am saying here? We cannot apply this recursion anymore if we get some t for which t of n divided by 3 to the power t is equals to 1. It stops there. Is it clear why we are assuming this thing? N over 3 to the power t is equals to 1?
And would it always be the case that we would assume that it's 1?
Yeah.
Or okay.
We'll assume for some t, we can stop this iteration. It will continue iterating until it hits something like that for which n over 3 to the power t is equals to 1. Then it will stop. Otherwise, it will continue iterating in this way. Is it kind of clear? No?
Yes.
Okay. So if we assume that, then we can write it, we can write the general form to the power n from this equation, from our general equation, this one. We can write that, we'll just replace I by t, and we will write that t of n is equals to t of n over 3 to the power t plus c times n over 3 to the power t minus 1 plus c times n over 3 to the power t minus 2, in this way all the way to c of n. So we have already assumed that t of c to the power, we have assumed this one, t of this thing is equals to 1. T of n over 3 to the power t is equals to 1. This is our assumption. So we can directly put that in this equation, and we will get that 1 plus c of n divided by t to the power t minus 1 plus c of n divided by 3 to the power t minus 2 plus all the way to c of n. Okay. And then we can write that 1 plus, we can take c of n as a common factor. Then we'll have 1/3 to the power t minus 1 plus 1/3 to the power t minus 2 plus all the way to 1. This thing is equals to t of n. Then we will consider that so this thing will be less than equals to c plus c of n plus this whole factor, as we have assumed that c is some constant which is greater than 0, which is actually greater than 1 or 0, some constant greater than 1. So if we replace this 1 with c, then it will be greater than equal to t of n. So we will get c plus c to the power c times n times 1/3 to the power t minus 1 plus 1/3 to the power t minus 2 all the way to 1 is greater than equals to t of n. Now for solving this inner factor, this thing, we'll solve that, and we will get that it is less than equals to 3 over 2. I'll show that derivation. So for now, let's just assume that it is less than equals to 3 over 2. Then we will get that c plus c of n times 3 over 2 is greater than equals to t of n. Therefore, we can say that t of n is equals to big O of n from this one. For some n greater than 0 and c0, c is equals to 5 and 0 is equals to 1. Okay, so now let me show the derivation how I am getting that. This factor is equals to 3 over 2. Okay, for that, we have this factor was 1/3 to the power t minus 1 plus 1/3 to the power t minus 2 all the way to 1. Right. So we are assuming that it is some series S, and then we will consider 1/3 of that series. We'll just multiply each term by 1/3. Then we will get 1/3 to the power t plus 1/3 to the power t minus 1 plus all the way to 1/3. Do you get how am I getting this second series?
You divided both sides by 3.
Yeah, exactly. Divided both sides by 3.
So you can actually can you write like s over 3 instead of,
Yeah,
is
yeah,
that the same thing?
yeah, exactly. That's
Okay.
exactly the same thing. Okay, now I will subtract s from s over 3. Then I will get, so these terms will get cancelled out all the way. It will also get cancelled out. And the only remaining term will be this one and this last 1/3 to the power t. So we will get 1 minus 1/3 to the power t. Is it clear how I'm getting this one? I'm just subtracting
How did t minus 2 get canceled?
t minus 2 because we will have another term here after this term.
Oh, okay, got it.
Yeah. Okay, so all of those terms will cancel out except these two terms, 1 and 1/3 to the power t, as we don't have any analogs for those terms in this series. Mhm.
Why does it have the power of t? I'm not sure of it. Oh wait, no, never mind. I see. It's the first.
Yeah, yeah. I just multiplied. Any other question, guys? Okay, so from this equation, we can write that we can take s as common factor, and we will get about t. So this is 2/3 of s is equals to 1 minus 1/3. 1 divided by 3 to the power t. So we can write s is equals to 3 over 2 of this entire thing. 1 minus 1 over 3 to the power t. So as we have previously assumed that 3 over t is equals to n. Then we can say that this will be equals to 3 over 2, 1 minus third of t. And even without considering that thing, we can say that this thing will be less than 3 over 2, right? Because as t is greater than 0, so this thing will be less than 1. This factor will be less than 1. So this entire thing will be less than 3 over 2. Do you get that part? How I am writing this thing?
Can you explain again?
So as t is greater than 1, according to our assumption, we assume that this thing is equals to 1. So as you can see, the value of this I was increasing as we were progressing through the iterations. So therefore t will be greater than 1, right? According to our this assumption here, t will be greater than 1. For some value of t, we will get this term is equals to 1. Is it clear? Is this part clear?
Uh,
I thought it was. I thought it was 1.
No, t is not 1. T is some value for which n t of n to n divided by 3 to the power t is equals to 1. So as you can see, this term is increasing as we are progressing through the iterations. It was 1 here, then it was 2, it was 3. So for some t, we will get t of n divided by 3 to the power t is equals to 1.
Okay,
So this
now
t
get it.
has to be greater than 1.
Okay, get it now.
Mhm. So given that t is greater than 1, so yeah, this thing will be less than 1. Do you see that?
Yeah, got it.
So we can write that this entire thing is less than 3 over 2. So from there, we can safely assume that the sum of this series S is less than equals to 3 over 2. Okay, and then we can put this value right there in our previous equation, for which we used to find the sum of t of n. So this thing is less than 3 over 2. So 3 over 2 times c of n plus c will be greater than t of n. Is this part clear? How we are getting this 3 over 2?
We got that 3 over 2 from what we did just now, right? Like
Yeah,
s minus
exactly.
s over 3.
From yes, this one.
Yeah.
There we go. So from that one, we can say that the sum will be big of n, as it is less than that for some c and n0. Okay, so it is one other way of solving that.
Wait, can you
Given.
go down to the answer again?
Okay. Yeah, this one. So yeah, this is one another way of solving that formula. You can use Master theorem because Master theorem directly gives you the answer. So this is one way of showing that Master theorem is correct
Mhm.
for this equation.
And all that stuff you did on the bottom, that was just to show how we got 3/2, right? Or
Yes, exactly. Exactly.
all that right there.
Yeah.
Okay.
Yeah. So this is one proof of master theorem. And you can also use another method called recursion tree to show the same proof. So it is also similar with this iteration method. So in this so for the same equation, T of n is equals to T of n over 3 plus C times n. We will draw the tree T of n. So first time when we divide this tree or put n over 3 in place of n, we will get C of n plus T of n over 3. Then in the second step, we will put 3 n over 9 here, or another n over 3 here. So it will be n over 3 times 3 or n over 9. So in that step, we'll get C of n times plus C of n divided by 3 and T of n over 3 square. In the next level, we will put another n over 3. In this way, the general term will be C of n plus C of n over 3 all the way to C of n over some 3 times I minus 1. And then we'll get n over 3 to the power I. So this is the same thing that we did iteratively before in this method. Yeah, same thing. It is just one other way of expressing the same thing there using the recursion tree. We'll get the same formula down there or same series down there if we consider the recursion tree. Is it kind of clear what we are trying to say? The recursion tree method. This is one other way of proving the correctness of Master's theorem. Then using this recursion tree method also we can show that Master's theorem is correct. We'll finally get this one. We have to just add all the nodes of the tree to get the final answer. Is it kind of clear? Okay, so let me give you one other example of. Let me give you one part of one code. So you have to find the recursion formula for that code. So this is one Java code for which we have public static void f of integer n, which is if given n is greater than 1, system dot out dot print ln still going. Semicolon, then f of n divided by 2, f of n divided by 2, then it ends right there. The function is there. Okay, so is this code clear?
Could you read it again? Just
Okay, so it is saying that public static void f of integer n. Then in this loop ends there. We have if n is greater than 1, then we have system.out.println still going, it prints something. Then we have f of n divided by 2 and f of n divided by 2 times. Then this if ends there. So you have to find the number of times the print function will be executed. You have to find one recurrence equation for this print
Why do
function.
why do we have 2 f of n over 2?
Yeah, it is just the function. So using this function, you have to find the recurrence equation for this function. Or in terms of n, how many times will it print? So it is a recurrence call for that function. Do you get that? For this function, it is the recurrence call.
Oh, yeah, yes, but why twice?
Yeah, it is just the program. There is no logic behind that.
Oh, okay.
So we have 2 minutes. You can discuss and solve it here. Or otherwise, I will give the answer after 1 minute. So do you see a pattern here? Or should I give the answer? Maybe it would be better if I give the answer. Anyone want to have a guess for the recurrence equation?
Would it be like C if n is less than or equal to 1?
No, you have to give the recurrence equation in terms of T of n. T of n is equals to something. Yeah,
maybe-
consider the Master's theorem, something a times T of n over b plus n to the power t. Something like that. You have to give the recurrence equation for this code.
we have 2 of t of n2
Mhm.
because we 2 times.
Yeah. Close, very close.
And then I'm thinking then the if statement is just a, I don't know, constant?
If statement, yeah, if statement is not the constant. Okay, so the constant will be this line. It is printing. So you have to find the number of times this program will print something on the screen. So it will print once for every n, and that for every n it will send twice and divided by 2 requests for to itself, recurrence twice, right? So in terms of master theorem, if we consider T of n, then we can say that T of n is equals to 2 times T of n over 2, as we are sending 2 f of n's there. For every n, we are sending 2 f of n over 2's, right? So A will be 2 and B will be n over 2. B will be also 2 because we are sending n over 2, right? From there, we are getting B. Do you see that pattern here? A is 2 because we are calling it twice. And B is 2 because we are sending n over 2. That's why B is equals to 2. Inside each function, we are sending 2 requests to itself.
Is that mean the 1 by 2, the b is a variable who is actually decrease or increase the value, who is one time create the boundary condition? I mean, the boundary condition will be false one time at the end.
Yeah,
So
yeah. At
that's
the end,
why
n will be less than 1. Then
that
it
is
will
the
stop.
reason we are using b, right?
Yeah, exactly.
Okay.
Then we'll stop when n is less than 1. And
Okay.
then for the constant, we are printing once. That's why the constant will be just 1 or n to the power 0.
Oh, the d, that is
Yeah,
representing the d
yeah.
part.
Because we are printing just once. Yeah.
Okay.
So we will get n to the power 0 2 times t of n over 2 plus 1. Because we are only printing once inside every iteration. So is it clear, guys, how we are getting the recurrence equation for one given program or Java code?
Why is D 0 again?
Yeah, because we are printing only once, so it is 1. So if we express d in terms of n to the power something, then as we are printing just 1, so it is n to the power 0. That's why it is d is equals to 0.
Okay, yeah. So I think the way I understand it is you're calling the function.
Mhm.
If comes into place and it's the statement system.out is
Mhm.
only called once.
Yeah,
And
exactly.
then since we're doing recursion, the
Mhm.
function gets called again down here.
Yeah,
But then
exactly.
that's something else. So we're only counting the n to the 0 as a 1 because you're only calling it once per function.
Yeah, we are printing once. That's why it is
Okay.
1.
In case if you are printing 2 times, in that case, d would have been something.
Yeah, d would have been something else.
Yeah, n
Constant
to
will
the
be
power
2.
2.
So
Okay.
actually, yeah, the constant would have increased if we have printed twice. It would have been 2 times n to the power 0.
Ah, okay.
Yeah, c
Okay.
times t. So t would have remained 0. Constant would have changed.
Got it.
D will be
So I
same.
hope you, yeah, any other question?
What would you have to do to get n to the 1?
It have to be something in terms of t or in terms of n. Suppose if we had something, some for loop for n or while loop, while n is greater than 0, print something, then it would have been n to the power 1.
Okay, thank you.
Yeah, as it is not a function of n here, so that's why it is n to the power 0. If it would have been a function of n here, then it would have been n to the power something, depending on that function.
If we print 2 times, and a D still be 0, right?
Yeah, exactly.
Okay.
It is,
Okay.
as it is not the function of n here. That's why. Okay, so I hope you all the best for the quiz tomorrow. So let me know if you have any other questions or something. I thought someone wanted to discuss one quiz question, right? No, one homework question.
Yeah, that was me.
Okay, okay. So I will stop recording and you can discuss that.
Okay.